So we were trying to do this surface integral. And we worked out that the problem with the surface integral of this piece of a parabolic cylinder is that I'm going to have to do 4 separate integrals. 3 of them have fairly nice normal vectors, but that 4th one, that upper surface, is just going to suck. So if I use the measure of flux, tell me how much of the vector field is coming in or out of this, by going through each surface, I'm going to have to do 4 separate integrals. That's disgusting. So instead, I'm going to try and do this as a solid integral. So we described this shape having a bottom and a top, a left and a right, a front and a back. Okay, according to the divergence theorem, instead of trying to do this vector field dot each of these different normal vectors, I can do the divergence on the whole thing. So I turn my surface integral into a volume integral. In order to do this properly, I need to compute that divergence. So somebody read to me, what is the vector field F? From what we wrote yesterday.
Plus sine z and z plus e to the x.
Ew. Except not so. Find divergence. This is 16.9. 16.9 was where we started with this statement of the divergence theorem with the top of this page. So this started 16.9. Just like we can write the curl as that cross product, I can write the divergence as a dot product, where that Nacho vector field, that's the dx, dy, dz. So this means I have to take the x derivative of which part? The first part. Wait a minute. What's the x derivative of this? 1. So y derivative of this? Z derivative of this? Okay, hang on a second. Before I go any further. What does the divergence measure? Figured out what the curl meant. The curl gave me how much of the stuff was rotating around that axis that our cross product gave us. So what's a divergence measure? Ben? Thought you were raising your hand. Okay. Kind of. That's what flux measures. Flow in or out from a point. So if I'm standing at a point and my divergence here is positive, it's telling me that stuff is going away. If my divergence is negative, it tells me stuff is coming in. If my divergence is zero, it tells me stuff is going through, in on one side, out on the other, equally. This divergence is positive, means more stuff is going out than is coming in. I don't have units for this. It's going to depend on what the units are for the vector field. But this is a constant. And that means that everywhere, no matter where I am, more stuff is going out than coming in. So I'm now going to do this triple integral to compute my surface integral. Instead of doing 4 surface integrals, I'll have to do 1 integral, and the integrand is 3. I'm integrating over this region. What order are we doing it in? Triple integral. I have to decide what order I'm doing it in. dz first. Or dy dx, because those are numbers, right? It's really irrelevant at that point. So if I'm going to do it dz dx dy, my integrand is 3. My limits in z are the bottom and the top. My limits in x, front and back, and my limits in y. Presto. You know how to do this integral. Please do. Again, I want to say, look at how much we've put together here. Surface integral for a particular type of vector field became a triple integral, and that meant I had to write out the region that I'm describing in my triple integral, decide the order of the integration, and now I have to do the integrals, but this is an iterated integral, and it's even nicer than that. When I do this first step, what do I get? Gives me. Hey, wait a minute. What can I do to make my life easier right here? Say again? I can take the 3 out, but I can take something else out. I can split the 2, right? How many y's are in there? So I could write the integral in dy, 1 dy, separate. Put the 3 all the way out here. If you want, you could leave it inside. You could pull it out. It's your call. You could have pulled it out right at the beginning, couldn't you? Because it's constant. You could put it all the way out right there. But now this integral is 3 times the integral of dy. I get a y evaluated from 0 to 2. So that's a 2. Here, what do I get? Thank you. From -1 to 1. All right, when you put in 1, you get 1 minus a third. That's positive 2/3. When you put in -1, you get -1 minus -1/3, which is -2/3, which means that gives me 4/3. That was a whole crap ton easier than doing 4 separate surface integrals, wasn't it? On our Canvas page, I posted an example of a surface integral. I think I labeled it Chapter 16, Section 7, Calc 3. Yeah, here it is. Surface integral example, Chapter 16, Section 7. And when we did that one, we were looking at the sliced at an angle piece. This thing. And I said, again, if we want to do that, we're going to need 4 surface integrals. The bottom, the left, the cylinder that's the top, and this angle the side. And I went through and I did all those surface integrals in that example. Disgusting. It's 4 pages. It's just 4 lines as a volume integral. The divergence theorem saves me a whole crap ton of time, especially when I'm looking at closed surfaces. Questions? This is Green's theorem. Green's theorem says I can go around the edge or I can do the inside when it's flat. Stokes' theorem says I can do that when it's curvy as a surface. But now I can do it when it's closed as a surface. Although I did say, for my version of the divergence theorem, that we needed a simple surface, right? No holes, no rips, no tears, nothing like that. It is possible to extend this idea to surfaces that have voids inside them. So here's one ellipsoid inside another. If I'm looking at the area between those 2 ellipsoids as my region, well, then technically I have 2 surfaces. I have the outside surface and I have the inside surface. And the normals point in different directions. Again, I don't want to do one normal inward, one normal outward. It's a pain in the neck. Why would I be wanting to do something like this? That particular picture is a button. That's capacitor. Metal film on the inside, metal film on the outside, and some sort of dielectric gel between them. And when you compress it, the spark can jump between them. This gives rise to an electric field discussion. I would love to tell you this is useless crap, but your touchscreen on your phone works because of this. It measures the electrical signal coming off of your fingertip. And when you touch it, you're compressing the dielectric. Useless. Never going to use it anywhere every day. Questions? We just said that if we have a positive divergence, then the vector field is going away. If we have a negative divergence, the vector field is going towards. So if I'm at a particular point, and I know that at that point, the divergence is positive, then I can think of that as a source of vectors. There are more vectors coming out than there are going in. And if I have a bunch of vectors going in, my divergence is negative at that point, I have a sink. Magnetic field. We have a north pole and a south pole, and we draw the field line going from one to the other, right? A source and a sink. It's exactly what the divergence is measuring. Again, as I said previously, sometimes you will see this written as F dot ds, where the S has the vector hat on it. I hate that version, but the textbook actually used it for this particular example, so I wanted to point it out to you that way again. Oh boy. Again, I'm asking for the flux of a particular vector field through the surface of this cylinder. So I have a can. Cylindrical side, flat top, flat bottom. I have a can. And I'm measuring the amount of signal that goes out or in to this can. Maybe heat. But the vector field is really ugly, so I'm pretty sure that's not heat. X times the quantity x squared plus y squared plus z squared. Y times the quantity x squared plus y squared plus z squared. And z times the quantity x squared plus y squared plus z squared. This is a disgusting looking vector field. I will learn to live with it. If I want to do this as a surface integral, what do I do? Which means I have to figure out how I'm going to write the sides of the surface, right? So I've got a top, a bottom, and then that lateral surface. Yes? So let's think about this. Top, bottom, side. Because it's a cylinder. How do I write the top of the cylinder? We'll go back and look at the surface itself. But it's not just the edge of the circle, it's the whole disk, isn't it? But it's the constant height of z equals 3. So I could describe the top, x squared plus y squared less than or equal to 4, and z equals 3. That's horizontal, isn't it? That's a flat z equals, that's a horizontal surface. That's a horizontal surface. What's the normal vector? Straight up. How about the bottom? Yeah, same thing as equals 0, but then what's my normal vector? Because it's negative because it points down. Why does it point down? Positive is going out from the volume. I'm going out. I'm at the bottom of the surface. Out is down. The side. Oh, because now my normal vector is going to be different in different directions, right? How am I going to describe the side of this cylinder? What function? That's how I describe the normal vector, but I have to describe the surface first, right? And I can only use, I've got two choices. I can either use the graph of something, the zx plus zy and 1, or I can describe it parametrically, r of u and v. This is a cylinder. The side of a cylinder. Is it a function? Can you write this graph as z equals something? Could you write y equals something? Or x equals something? Well, no, because it would not pass the vertical line test. It would go to 2 to 1. It's a circle. So I got to do this parametric. I got to do this as an r of something. We did a cylinder already once. How do I describe this cylinder? All right, wait a minute. This is the cylinder, x squared plus y squared equals 4, and 0 less than or equal to z less than or equal to 3. It's the side of the cylinder, right? Side of my cylinder. Okay, here's the side of my cylinder. Now what? Picture the grid, right? We have a grid on this cylinder, a checkerboard. Part of that checkerboard is going to be described going up and down the cylinder, yes? Part of the checkerboard goes this way. That's z. So z is one of my parameters, which means the other parameter should be describing the part of the checkerboard that goes this way, around the cylinder. What's the best variable to use to go around the cylinder? I'll go around in terms of the angle, right? What's the radius of the cylinder? So the only thing that has to change is theta. So I can use my parameter theta for x and y. And that will describe the side. Now to do the normal vector, I'm going to have to do that RU cross RV, but I don't have U and V, so it'll be R theta cross RZ, where R R of theta and Z is 2 cosine theta, 2 sine theta, Z. So R theta cross RZ is now something I can compute. And then I'll do the length of that, and that'll give me the normal vector, and I'll be able to do this integral, right? Holy crap. If I want to do the surface integral, this blows. This is a horrible setup, isn't it? I've got to do 3 separate surface integrals. I've got to rewrite my vector field in terms of R, this is X, this is Y, this is Z. Oh my God, I'm going to be in trouble, aren't I? I don't like this. I don't want to do this. But since I'm asked to find the flux, I can use the divergence theorem instead. I'm looking at a cylinder. It's a simple connected region with a bounded inside. I can do the divergence theorem. Let's try that instead, rather than doing 3 different surface integrals. And that's the whole reason I went through setting this up. Oh, I'm going to do a surface integral. Let's do the surface integral. Oh, this is ugly. I don't want to do this. Let's try, see if the other way is simpler. Maybe the other way sucks just as much, and this is actually the easier way. I don't know yet. Let's try it. But that means what I need is I need the divergence of my vector field. And remember, the vector field itself is this thing, F. What's the divergence of that vector field? This is going to take a few minutes. I got to do the product rule 3 times. Fortunately for me, it's symmetric. The way you do the product rule in X on the first piece is the same way you do the product rule in Y on the second piece, because those changed. And it's the same way you do the product rule in Z on the third piece. So when I actually do this, P with respect to X, I get 1 times X squared plus Y squared plus Z squared plus, leave the x alone, do the derivative of this part with respect to x, that's just 2x. When I do the derivative of the second term with respect to y, I get 1 x squared plus y squared plus z squared plus, leave the y alone, do the derivative of this with respect to y, that's a 2y. See the symmetry involved? When I do the z derivative, I get 1 x squared plus y squared plus z squared plus, leave the z, derivative of the inside is 2z. Please notice I have the same thing 3 times. I have x squared plus y squared plus z squared 3 times. 1, 2, 3. So I don't have to worry about the rest of it. That's 3 x squared plus y squared plus z squared plus. What's the rest of it?
In parentheses, x squared plus y squared plus
2x squared, 2y squared, 2z squared. But wait a minute, that's just 5 x squared plus y squared plus z squared. That actually does look a little nicer. But there's even another reason I'm happy to see this. Why am I happy to see this? Because I'm doing a 3D triple integral on a cylinder. If I'm integrating on a cylinder, what coordinate system should I use? Which means the x squared plus y squared is a nice easy thing. Somebody get on their computer, see if they elected a pope. Okay, then that's what that is. Yeah, now, and see, now Zoom is asking me if I'm playing music. No, I'm not. There's just something in the back. Go away. Okay. So now I need to do the triple integral over the cylinder of this thing. We're celebrating our divergence. No. Absolutely. Yes. I just think that that's going to give me more pieces to add and worry about, but it absolutely does work. It should end up being the same here. So here's my question. If I'm switching to cylindrical to polar coordinates, what's my description of the cylinder? R theta and z, right? Good. We're celebrating. We have a hope. We should celebrate. Sunday, right? Right before finals start, we'll have a papal bash. Why not? I don't remember what we did when Francis was elected, so I think we had nice. Anyhow, what are my descriptions for my cylinder? Advantage, you already have all this information in the way we set it up.
0 to 2 for R, 0 to 2 pi for theta, and 0 to 3 for z.
My cylinder goes from height 0 to height 3, and it goes all the way around. Perfect. I love it. This is great. Fabulous. Why am I really, really, really happy now? Because that's a freaking box. They're all numbers. So in order for me to set this up, let's see, it's DV. What's the DV part? What order do I put those in?
Already paid. And easy.
And a DZ. You can put it in any order you want because they're numbers, right? I put the Z first, you don't have to. You can put the R first, it doesn't matter. But if I put the Z first, then this goes from 0 to 3, R goes from 0 to 2, and theta goes from 0 to 2 pi. What goes in here as my integrand? I wonder if there's a reason for how many. There have been a lot of pokes, right? Maybe they're ringing one for each, I don't know.
5, and then 2 cosine squared. Plus 5.
Oh, that's gonna get really big, really ugly, really quick, isn't it?
We can just.
It could be just,
Wait, no.
I'm confused.
um,
I've got an x squared and a y squared. X squared plus y squared is r squared. Z doesn't change, so I get that. Okay, I can pull the 5 out. And then I would have r cubed plus rz squared dz dr d theta. 0 to 3, 0 to 2, 0 to 2 pi. Presto. This is an easy integral. So do it. It's not short, but it is easy. For those of you interested, Leo the 16th, Pope Leo the 16th is an American, the first American Pope ever. Robert Francis Prevost. I'm sorry, the other. So when I integrate with respect to z, I get r cubed z and r z cubed over 3. Put in 3, put in 0. Well, our 3 cubed is 27, but then I get 3 times z cubed over 3, so the 3 on top and bottom cancel. 27z minus z cubed. What can I do with the theta at this point? My buddy Fubini allows me to take these two integrals apart. 5 integral 0 to 2 pi d theta, integral 0 to 2, 27 z. Wait a minute, that's wrong. What did I do wrong? Somebody stop me. Figure out why I did it wrong. This is not right. This is z equals what? So what happens when I'm working too quick, I put it in the wrong variable. Okay, let's plug it in the right place. 5 integral 0 to 2 pi integral 0 to 2. I plug in for z. So I get 3r cubed plus 27 over 3, 9r dr d theta. I still separate it. I just have to, I'm looking at this, I'm going, how am I getting an integral of z dr? I've screwed something up. See, makes sense. I got z's, but I should have a dr. That doesn't work. So 5 integral 0 to 2 pi d theta, integral 0 to 2, 3r cubed plus 9r dr. Now that's the right letter. That goes with that. This gives me a 2 pi. What does this give me? Almost. And that's evaluated from 0 to 2. So 5 times 2 pi, 2 to the 4th is 16. 16 over 4 is 4. 3 times 4 is 12. 2 squared is 4. 4 over 2 is 2. 9 times 2 is 18. 30 times 10 pi is 300 pi. More stuff coming in or going out? Because this flux is positive. We're going out because that's the direction of our normal. Our normal was pointed out, we're going out. By the way, this is not the way I did this in my notes. In my notes, I did dr d theta dz. I got the same answer, doesn't matter. This is numbers for my region, I can do it any order I want. .9% of the time, if you are asked to use the divergence theorem and you're given a surface integral, you're going to want to do the volume integral. It's much harder to go the other way. If you're given the volume integral to then turn it into a surface integral, means you have to find the vector field whose divergence is the thing you are given. That's really hard. I know how to find a vector field whose curl is the thing I am given. I can kind of work my partial integrals backwards, but it's still very difficult. So more often than not, we will be working from the surface to volume with the divergence theorem. Question? There's the definitions of sink and source again. If the divergence at a point is positive, the flow is outward, that's a source. The divergence is negative, that's a sink. So here, I have a point. More stuff is coming in than going out. They use proportional vectors. That makes this a sink. More stuff is coming out than going in. That makes this a source. Tomorrow's question and answer day. So bring your questions, and then Monday the homework is due. I'll see you all then. It works. We made it.